Yeah, hello. So, in the last session we looked at how to represent data by looking at abstract data types and a few of the particular abstract data types like stacks, queues and linked lists. So, the advantages of implementing these data structures or data types using arrays, and also looked at advantages, disadvantages of representing them using linked lists. We also had observed that the particular data types that or data structures that we looked at earlier were useful when the data had no relationships between them. And so, we looked at what were called linear data structures. So, this is something we just looked at in the last session, where stacks, queues and representation using arrays and single linked lists or double linked lists. So, question is, how do you represent data which is going to have relationships or which are going to have hierarchy in the representation, and that is what we will try to concentrate on in this particular session. Let us look at data structures which allow us to capture relationships and represent them in our model. So, the structure that we are going to look at, the first nonlinear data structure that we are going to look at is going to be tree. There are a few more that we are going to study as we proceed in this particular course or as we go ahead in this course. We will introduce them as we require them for our applications. So, the first nonlinear data structure that we are going to look at is going to be a tree. So, as the name indicates, tree, the analogy comes from the tree, where you have a tree which has branches and more branches branch out from other branches. So, examples of tree typically you have are, if you want to represent hierarchies in an organization where more than one people report to the same person, and this can happen recursively. And finally, at the top you have probably a vice president or a CEO or a owner of the company, which we are going to look at as something like this, which is sits at the top of the tree. So, if we look at precisely the structure that we have in this slide, we have a hierarchy in our relationships. There are relationships and there is a hierarchy in the relationships. The one we have here in the slide is a family tree. Right. So, family tree, as we see, we have the root of a family tree and we have the relationships between the members of the family. So, we know that Anne and Amy are related and Eva and Guy or Jan is related to Guy. So, such relationships can be caught in this particular tree. Many examples are, you have the way we maintain our files in a memory or in our machines. Right? We have folders, then we have subfolders, within subfolders we have we have files and so forth. So, that precisely is a relationship between the data sets or data items that we want to maintain. So, this structure resembles branches of a tree, and so the name. So, the name comes from the natural meaning of a tree as we understand in our daily applications or daily understandings. So, let us try to look at how to define these trees in abstract or a definition of a tree. So, tree, as we saw, is going to have nodes. Nodes are something like this, and then there are edges which connect nodes, and one of the important property of a tree is that between any two nodes there is precisely exactly one path. Right? So, if I look at any, say, particular this node and this node, then the path that we have is a unique in this particular tree. Right? So, trees will have nodes and the nodes are going to be connected by edges. So, nodes are the entities that we want to represent. Okay, the nodes can store or represent a number, it can represent a name, it can represent name of a file or name of a person as what we want. Edges show the relationships that they have between each other, and between any two nodes we will have exactly one path connecting them. Let us look at some more definitions of a tree. The trees that we would be interested, we will have a root which is specified by the user, correct. In this particular case, this a node which has nothing. If I look at the geometric representation, the way we are represented, root has nothing above it. So a node which is like this, which has nothing above it in the representation, will be called root, which is decided by the user. Right? So in a organization, the root node can be the director of the organization. So once we identify this root, our tree will be called a rooted tree. And after that, once we have a root which we say is at level 0, then we can specify levels for each other node into the tree. So if you look at this, so this root has a level 0, then all nodes at this level are at level 1 and so forth, and if I look at roots at this, they are at level 3. So once we identify a root of a tree, we can associate levels to every node of a tree. The root will have level 0, the nodes which are connected directly by an edge to a root will have level 1 and so forth. We also identify a few more nodes. So the nodes which are like root or which are like this, which certainly have nodes below them in the hierarchy, will be called internal nodes. So nodes which has elements which are lower in the representation will be called internal nodes. When we say lower, we look at the graphical or the geometric representation of a tree, where we are drawing it top to bottom. So the root is at the top of the tree, which is level 0, and then we go down the tree. So when we say up and down, we are looking at the geometric representation that we have in mind when we define trees. We also identify a few more relationships other than the internal nodes. All nodes which have such relationships, correct. If I look at these two particular nodes, this is in the representation upper than this particular node, we associate a parent-child relationship, as we would do this in a family tree. So if I look at my previous example of the family tree, this is an example of a family tree, and if I look at this relationship between the two nodes, then we know in the family tree the relationship is of a parent and a child. So if something is above something in a family tree, then we say this node is a parent of this particular node. Or if I look at this, we will say that this node is a child of this particular node. Correct. So in a family tree, what understanding we have about the nodes with the parent-child relationship, we define or we carry that understanding or notation to a general abstract tree. So that is what precisely has been said here. So in this general abstract tree, we have a parent-child relationship between this node and this node. So we will say this node is a child of this and this is a parent of this. Also nodes which are at the bottom of the representation or which does not have anything below that will be called external nodes or leaves. So we will call this as leaves, or we call them as external nodes, unlike internal nodes. Internal nodes are the nodes which we seen has something below them in the representation, or now in more technical term, we will have a node which has a child will be called an internal node. A node which has no childs will be called an external node or a leaf. That is, there are nothing that is going to branch out from there. So these are the few more basic definitions that we are going to use in practice. So I will just quickly repeat them once. So root is to be identified by the user, that is at level 0. Once we associate a root, we can associate levels to the all the other nodes in the tree. Then you have external nodes and internal nodes, and the relationship is the parent child relationship. The terminology we carry forward from our understanding of a family tree. A few more terminologies as we are going to work extensively with trees. As we said, the nodes of a tree represents the data that we want to store, correct. So, whatever data that we want to represent can be stored in a node. A node also would be called a vertex. We already said this, the first or the topmost node or a vertex will be called a root node. The relationship are going to be represented using edges. A path is a list of distinct vertices in which successive vertices are connected by edges in the tree. Right. So, path is just, if you look at two nodes and look at right. So, if I look at the previous example, so if you look at this particular node and this particular node, this precisely is the path from this node to this node. Right. So, we can also define a path. The key property is that there is a unique path between any two vertices. This also would mean that your tree does not allow cycles. Right. So, something that we are going to define and use extensively as we add more restrictions on our trees. Again, as we use this in practice, a disjoint set of trees is called a forest, and nodes with no children are called leaves or terminal nodes or external nodes. A few more terminologies that we would be using as we go ahead. We have already seen a child and parent relationship. Another key idea that we are going to use is what is called a subtree. So, subtree, before we look at definition of subtree, we also carry over our understanding of family tree to a general abstract tree. As we recollect in a family tree, let me go back to an example of the family tree that we had. Yeah, so this was an example of a family tree. If you look at this particular node and this particular node, we know this is a parent and this parent is here. So, we say that this particular node is a ancestor of this particular node. So, if you look at this particular node, this is ancestor to all the nodes in the tree. So, as we use in family tree, the understanding of ancestor and descendant will be carried over to a general tree. Like parent child, we also going to carry ancestor and descendant terminology from our general understanding of family trees to trees in general. So, now if I look at a subtree, we look at a subtree rooted at a particular node of a tree, and along with that all its descendant will be called a subtree. So, if I look at this particular node, so this node along with all its descendants will be called a subtree rooted at this particular node. Right. So, a subtree rooted at a particular node would mean that node along with all its descendants. Idea of subtree is going to be very crucial in a lot of applications that we are going to do. We also defined along with levels, so what is something called as a depth. So, depth of a root node is always defined to be 0, and depth of any other node is 1 greater than the depth of its parent, correct. So, you look at, so the root is at depth 0 or level 0, and if you look at any other node, you look at depth of its parent and add 1 to it. It is a very intuitive natural definition like level. So, we are going to use level or depth in our understanding of where exactly the node is going to lie in the structure tree. The size of tree is just going to be the number of nodes that you have into the tree, and very important idea is going to be the idea of a height. Is you look at all nodes and their depths, and the one which has the maximum depth will be the height of the tree. If I look at an example, right. So, if this precisely is a tree. Now, if I look at this, this has depth 0, all this has depth 1, this has depth 2 and this has depth 3. So, we will say height of a tree is precise. So, height of this particular tree is 3. So, what you do is you will write down the depth of each node. The one which is going to be the maximum is going to be defined as the height of the tree. Just as along we use in family tree, if two nodes share a common parent, we are going to call them as siblings. So, siblings are nothing but nodes which share a common parent. That is again something that we use when we talk about family trees. So, presently we are going to be interested in a very specific type of trees which are called binary trees. So, in a binary tree it is either empty, that means it does not consist of any node, or it consists of a root together with two binary trees called as left subtree and a right subtree. So, if you look at the definition, it is a recursive definition. To understand in a simple language, every node other than the external node is going to have at most 2 children. Right. So, rather than looking at the recursive definition, this definition is simpler to understand. But as we will see in practice, the definitions which are easy to understand may not be very easy to implement, whereas recursive definitions are easy to implement because what you have are what are called repeatable arguments. So, you can write down a function and you can do a function call and repeat and implement it. So, many definitions that we understand easily without recursive would be implemented easily by doing recursive definitions. So, if I look at this definition, it is a recursive definition. So, you have a root and with two binary trees called a left subtree and right subtree. So, if this is your root, I am going to call this as the left subtree and this I am going to call as the right subtree. Right. So, in sense what we are saying is a node has at most 2 children. So, as soon as we have at most 2 children, we can associate an order to it as left and right, as we do in practice. So, this will be called the left subtree, this will be called a right subtree. So, binary tree recursively would mean every node will have a left subtree and a right subtree, or we can say that every node can have at most 2 children. So, in this case every node has only the right subtree, the left subtree is empty, there is no left subtree here at all, it has only the right subtree. So, binary tree is a specific type of tree in which every node has at most 2 children. We will see that binary trees are very useful in representing lot of applications, data, and can be extensively used in solving problems. Some simple properties of a binary tree. I am going to just use this notation again. N is just going to represent the number of nodes in your binary tree. N subscript E is going to be number of external nodes, N subscript I is going to be number of internal nodes, and H is going to represent the height of a tree. With this notation, we have the following 4 results. So, the results are very simple to prove. So, I will just try to give a small we will just try to give the outline of the proof. So, let me look at the following example. The results that we are trying to prove are for specific type of binary trees which are called proper binary trees. In this case, every internal node has exactly 2 children. So, you have a tree like this. So, every internal node has exactly 2 children. So, this is a proper binary tree. Now, with this particular representation of N, E, N, I and H, we can prove the following 4 things. Now, if you look at the number of external nodes, correct. So, number of external nodes in this case we can see is this 4. Now, if I look at the height of this particular tree, then this is at depth 0, this is at depth 1, and these are all at depth 2. So, height of this tree is going to be 2, and it is easy to observe that h plus 1. So, h is 2. So, h plus 1 is 3, you have 3 is less than equal to 4, and this is less than equal to 2 power h is going to be 2 squared, which is 4. Right. So, this result which we have seen empirically can be easily proved in general. What we need is the following observation, that in a proper binary tree, if you look at a depth h, right. So, for example, if I look at depth 0, you have precisely 2 power 0 nodes. At depth 1, you have precisely 2 power 1 nodes. At depth 2, you have precisely 2 power 2 nodes. So, at depth h, right. So, I can generalize this, at depth h there will be precisely 2 power h nodes. So, all these results that are stated here 1, 2, 3, 4 are basically proved easily by using the fact that at depth h you have 2 power h nodes. Once you use this idea, all the results are very easy to prove. We have already observed this in result 1. Once you prove result 2, result 3 is just nothing but 1 plus 2. Right. So, once you prove result 1 and result 2, you just add the two sides and you get result 3. And again, if you find the height of tree in terms of the nodes, it is very easy to observe by using the same fact that. So, if you look at this, number of nodes that you can have is, you can sum this up, correct. So, if I want a number of nodes, let us try to look at the last property, right. So, you look at the so what you want is a relationship between h and n, that is, n is the number of nodes in your tree, h is the height of the tree, and it is captured via the following relation, correct. So, n is nothing but 2 power 0 plus 2 power 1 plus 2 power h, that is the relationship which is captured in this expression. The relationship between n and h is captured in this expression, and then you can use our standard, this is nothing but the geometric progression, and then this becomes 2 power h plus 1 minus 1. So, if I now just work with this equation, precisely you will get the last property. So, all the 4 results are basically based on only one key observation, that in a proper binary tree at height h, you have 2 power h nodes. We are also going to be interested in this particular type of complete binary trees, in which all the levels except the last level are completely filled, and at the last level all the nodes are filled from left to right. What that precisely means is, if I look at this particular example, all the levels except the last level here is this, they are completely filled. That means except the second last level, all the other nodes which are at internal, which are at levels other than the second last level, will have exactly 2 children. At the second last level, all the nodes will have exactly 2 children, and they will be filled from left to right. In a complete binary tree, we can use array to represent it. Right. Finally, once you have a relationship in a structure, and which we have geometrically represented as a tree, has to be captured in machine. Now, we can use arrays to capture this relationship. So, complete binary tree can be represented in memory by an array, so that access become very fast. We know array access is very fast. So, we are going to label nodes sequentially, top to bottom and left to right. Left child of ai is going to be at position a of 2i, right child of ai is going to be at position a 2i plus 1, and so this is also carried out. Parent of ai is at ai by 2. Right. So, what we are going to do is the following: we are going to label the nodes as 1 to n, top to bottom, left to right. The hierarchy that we are going to follow, or the order that we are going to follow, is top to bottom, left to right. Once we do that, we capture the parent-child relationship using these two properties. Left child of AI is at position A2i and right child of AI is at A2i plus 1. Let us illustrate this idea with an example. Correct? So, I have a complete binary tree in which we have labeled, if you see all our nodes top to bottom, left to right. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I had ordered them as 1, 2, 3 would have been a wrong order, because we are labeling this top to bottom but not left to right. This is top to bottom but right to left. So, such a labeling is not allowed. We have to follow precisely the labeling as suggested there. Now, we can represent this as an array. Okay. So, I have level elements. So, the root is going to be at A0, which is going to be 14. Now, its child, the left child is going to be A2i, which is going to be here, and the right child is going to be at 2i plus 1, and I simply carry out this convention now. Now, if I look at 10, its left child is going to be at level 4. So, this is 1, this is 2, 3. So, this is 4, and right child will be at location 5, and you carry this on. Now, I look at the third location, this is here, its child, left child is here and the right child is here. So, that is 6 and sorry, this is 15 and 18, and I can continue this. Okay. Once we know how to do it, it can be easily observed. Now, given such an array, we can easily construct this tree. Okay. So, I can start by looking at the first element 14. I know this is the tree, the root of the tree. 10 and 16 are going to be the left and right child. 8 and 12 are going to be the left child and right child of 10, and so forth. So, given a complete binary tree, we can represent this using an array, or given an array, we can do the reverse operations and can find out the complete binary tree, which is going to be represented by that array. We also know that array has its own disadvantages. Though access is fast, we know resizing is a problem with arrays. So, one can represent binary trees also using a linked list representation. Now, in a linked list, we know we were using a doubly linked list where we had data and 2 pointers to the previous and to the left. In this case, we are going to require more fields at a particular node in a linked list. It will require a field which will store what information it has to store, and it has to remember 3 things along with the information. One is what is the parent and what is the left child and right child relationship. So, every binary every node is going to remember the left, the right and the parent along with the information that it is supposed to hold. The only node, the root is going to have a parent pointer as null, and the leaves will have the left and right pointers as null. So, using this convention, we can look at the following example. So, this is a particular node, this is the root node, its parent is pointing to a null pointer. It is going to store information about what data it has to have. It is going to point to parent, then it is going to point to its left child, and it is going to point to its right child, and this precisely is the information that you are going to store in that particular, which is the name of a town. So, every node will have at least 4 fields. One is parent, one is left child, right child, and the information that we want to store. So, using this structure, we can represent the tree. Once we represent this our data as a binary tree, or in general any other tree, it is important that we should be able to access this nodes or access this information. That means, we should be able to traverse into a tree. Now, there could be many ways of traversing. In fact, there are 6 ways of doing this. You can first go to the root, then the left child and the right child, or I can do root, then right and left, or you can go first to the left, then the root and then the right, which is called in order, or this, and I can go to the first to the left child, then to the right, and last to the root. Right? So, suppose I am going to represent this as a tree. So, let us try to look at what this means. So, I can first visit this, then this 2, or I can do this and then this 2. That is the first line. The second is I can first visit this, then visit the root and then visit the node. So, there are many ways of traversing a tree. What we have done is just shown 6 of them. There can be more than 6. One can do even such a traversal. You can first traverse all at level at the last level, then the second last level, and so forth. Or I can start from first traverse all the nodes which are at level 0, at level 1, level 2, and so forth. Right now we are trying to look at precisely, we are going to concentrate on this 3, that is a particular way of doing it. So, root left right, or left root right, or left right root, and we are going to call them as pre, because this is going to be decided when we actually are going to visit the root node. This is called pre-order because root is visited first, in order because root is visited in between left and right, and post because root is going to be visited last. That is a simple example. We have been, so pre-order is going to be first root, then left, then right. In order is going to be first left child, then root, and then left child, right child, which is 2, 1, 3, and post order is going to be first this, then this, and root at the last, which is 2, 3, 1. Right. So, this definition just illustrates this for a small tree. The general definitions are just going to be the recursive definitions. Right. So, if I have more complex trees or bigger trees, I am just going to repeat this at all particular nodes. So, the definition is going to be recursive in general. So, let us try to look at the general definitions. The in order traversal. So, first visit left subtree, then the root node, and then the right subtree, correct. So, if we want to label this or traverse this tree in a in order traversal, first we are going to traverse this, which is the left subtree, then we are going to traverse the root or visit the root, and then traverse this, and this definition is going to be recursive. Now, if you want to traverse this particular tree, then we are going to first traverse the left subtree, then we are going to visit the root node, and then we are going to visit the right subtree. Right. So, these definitions, as we said, are recursive. So, that is in order traversal. Similarly, we are going to have post order traversal, that means first the left subtree, then the right subtree. Sorry, this is pre order. So, first the root. So, we will first visit this, and then visit this in pre order, visit this then in pre order. So, visiting this in pre order would mean you will first visit this, and then you are going to visit this in pre order, and you are going to visit this in pre order. Right. So, the definitions are recursive. I think as we work out an example, the definition should be more clear, and then you have the post order traversal, correct. So, let me illustrate this with an example that should be easy to understand them. Right. So, I have a little more complex tree, and we are going to try to traverse this in the 3 orders. So, the pre-order traversal, if you recollect, pre-order traversal is first root, then left subtree, right subtree. Right. So, you will first traverse A. Right. So, let me take this. Then you are going to traverse the left subtree in pre-order. Right. So, the left subtree is here. I am going to traverse this in pre-order. That would mean first I am going to traverse the root of this, and then you are going to traverse this in pre-order, and then this in pre-order. Right. So, you have already looked at A and H. Now, this in pre-order there is only one. So, you are going to represent H, and then now you are going to traverse this in pre-order. In this you are going to first traverse I, then F, and then E, correct. So, what you have done now is you have traversed the root in pre-order, and you have traversed the left subtree in pre-order. The same idea now will be, or the same principles will be used to traverse the right subtree in pre-order. Correct? So now I look at the right subtree. So first you will traverse B, then C, and then D. Correct? So that's precisely the pre-order traversal. The post-order traversal is first the left, then the right, and then the root at the last. So in the post-order, first you are going to traverse the left subtree, then the right subtree, and then you are going to traverse the, this A is missing, so I will just add A here, and then you are going to traverse A. Now first you are going to traverse the left subtree in post order. That would mean you are going to traverse this first in post order. Correct? Now recursively I am going down, so that would mean first I am going to traverse G. Correct? Before you visit H, you are going to traverse the right subtree of H in post order, which is going to be F, E, and I, which is here. Then you will traverse H, that is the root. So at this particular juncture, you have traversed the left subtree in post order. Next you will traverse the post order traversal in the right subtree, which will come as D, C, B, and finally A. Right? That's a typo, I have just missed A, I am adding it here now. Right? So post order will be A at the end. Right? So just sorry for the typo. Similarly, let me look at the in order traversal. In order is left, root, and right. So in order would be first traverse this in order, then go to the root, and then traverse this in order. So I will leave this now, not work out the details, but it is easy to see that the left subtree, whatever are as they are visited in order, then you are going to visit A, and then to the right are you are going to visit in the nodes of the right subtree in order traversal. So if you are given this and you are told that this is in order traversal, we know precisely if I am going to have A node, then these are all in the left subtree and these are all in the right subtree.